cost engineering or financial. He has published in the best journals both in the field of statistics and its application in health. The title of his talk, Functional Data Method for Wearable Device Data, is closely aligned with the idea of our workshop. If you do, Jeff, go ahead.
Great. Thank you very much for the introduction and for having me here. Of course, I would much prefer to be joining everybody in person, but it's a real pleasure to be able to tell you a little bit about the work that I've done over the last few years. I am going to talk today about functional data methods for wearable device data, and in the spirit of thinking about how to build bridges between these approaches and data science, I'm also going to talk a little bit, if there's time, about work that I've done to develop an R package that is helpful for working with functional data. I want to acknowledge at the outset that my plan for today's talk is to try to talk about a lot of problems that I've worked in and give some idea about what models can be fit, what's possible to learn from wearable device data, and in broad strokes, how you might go about fitting some of these models. I am going to omit a fair bit of the technical details, although if there are questions about this or if references would help, I'm more than happy to share those as well. Since I'm going to be covering actually quite a bit of ground, there are a variety of acknowledgements that I want to make here at the outset. I've been happy to work with a variety of collaborators on a number of the projects that I'll point out, and I'll do my best to note who I've worked with on what as I go through, but here's sort of a list of a great many people who I've had the joy of working with, as well as the sort of acknowledgement for the funding agencies that have supported this work. I also want to acknowledge that we're going to be looking at data from a variety of different studies, and I'm both grateful for the ability to work with those stakeholders and collaborators around that, and also the participants in those studies who gave their time and energy to produce high quality data that allow us to understand a little bit better what's going on with physical activity and health. And that comes, for example, from the Columbia Children's Center for Environmental Health, the Masked Hypertension Study, and the Baltimore Longitudinal Study of Aging. Folks are probably at this stage fairly familiar with wearable device data. What these look like often are Apple Watches or Fitbits, and I think that's a useful framework for understanding what wearable device data often looks like. Many times we use a more research-grade device, but the idea is that there will be a wrist-worn or sometimes a hip-worn or some other location-worn device that measures, roughly speaking, how much that device moves and how much it accelerates. There are a lot of these things on the commercial market. Some of them on the commercial market are better for some research purposes than others. There are also a variety of research devices that include not just wearables, but other ways of extracting biosignals. What we see here is a chest-worn device that gives both accelerometer measurements and also heart rate measurements, so one can understand sort of the joint association between physical activity and heart rate in real time. I've worked with a group in hypertension, and this group very often gets data using a wearable device that gathers data less frequently, about once every half hour, but it gives you an idea about blood pressure. So you'll see the gentleman is wearing a sort of a pouch here as well as a blood pressure cuff, and every half hour or so the cuff inflates in the same way that one would have their blood pressure measured in a clinical setting. More recently, there's interest in thinking of other kinds of devices that are not intentionally set up to be wearables, but they can be used in this way. Things like a phone, something that is kept on or near the person almost the entire day, and it can give insight into both physical activity, but also other kinds of interactions that can be used both to monitor how somebody is interacting with folks socially, be a platform through for which interventions can be disseminated, reminders to move, questionnaires, things like this. Accelerometers are what I'm going to focus on primarily, and the reason for that is much of the work that I do in public health is focused primarily on things that have to do with physical activity, how often somebody moves, whether or not they're getting the recommended amount of exercise and things like this. Historically, physical activity, although it's extremely well known to be important in many problems that involve health and many health issues, it hasn't been a particularly easy thing to measure up until maybe 10 years ago with the advent of these wearable devices. Often the way that physical activity was measured was through retrospective questionnaires. Somebody would ask, how much activity have you gotten over the last 2 weeks, or something along those lines. And that's a very difficult question to answer for an individual, and it's one that's difficult to trust as a researcher. And so accelerometers have become hugely popular because they are at least relatively unbiased. The device is worn and it sort of measures acceleration in a somewhat objective fashion. And I'm sort of putting objective here in quotes and roughly unbiased in quotes because I don't want to mask the fact that there are issues with the devices, that sometimes they can gather data incorrectly, that there are issues of distinguishing inactivity from somebody taking the device off and setting it down. There are a variety of issues that go along with wearable devices, but in comparison to what had gone before, these are very, very, very well-known or well-structured ways of getting unbiased information about physical activity. The kinds of data that are produced look something like this. This is a plot of 420 kids in northern Manhattan, the Bronx, and we're looking at their physical activity over the course of 24 hours. And we see, in the nighttime, actually, I apologize. This is a study of elderly patients living in and around the United States. And so we see, in midnight and in the nighttime, people are generally less active. During the daytime, there is an increase in physical activity. There are occasional large outliers indicating perhaps that somebody has engaged in some form of physical activity. But this is the kind of information that we see. For every participant and every day that the device is worn, we have one observation per minute, and sometimes a little bit more frequently than that, information on each of these subjects. We occasionally will take that raw output and transform it into a binary active or inactive categorization. And in this sense, this reflects an interest and awareness in the idea that very frequently it's not so much the intensity of activity, but just the presence or absence of activity that's important, that sedentary behavior is a real driver of adverse health outcomes. And so just understanding whether or not a person is active or not can be important regardless of the magnitude of that activity. This is a plot sort of similar to the spaghetti plot I showed a second ago that shows all of the activity for every subject in this sort of binary time period. And so here we saw, binary view. So we see again that people are often inactive in the nighttime and then become more active during the day. So I'm going to talk a little bit about functional data analysis, at least as a way of thinking about these data and building models to understand their structure. Functional data analysis is not the only way that one might approach accelerometer data or other wearable devices, but it is the framework that I sort of find most natural and also the one that I've done a lot of work in from a statistical perspective. So this is a preference of mine that is not necessarily a requirement at all for analyzing wearable device data. Generally speaking, I think about functional data as observations on a subject that are subject-specific, x sub I, measured over some time interval t. And that can be subject-specific, often it isn't, but you have a continuous observation for each subject I. And so in the context of physical activity, I'm sort of thinking of the underlying process, physical activity measured over 24 hours is a continuous function. And I have an observation of that function for each participant. I have one functional data point, one complete curve for each subject or for each day. And in that case, we do in fact see exactly the same grid for everybody, sort of midnight to midnight as an analysis framework. This functional data notation is largely conceptual, and what I mean by that is you can think about physical activity as a continuous process, but when you actually go to observe functional data, very often you get observations on a finite grid. Here we have 1,440 minutes in a day is often what we're going to be looking at. This, again, I think works well as a framework for thinking about conceptualizing wearable device data and physical activity in general. So if you're interested in doing functional data analysis, or you're thinking of the data that you have as functional, then there's a need to start doing some kinds of statistics on those things. And you can think about defining a mean or a covariance structure for these. And I'm going to talk in this presentation about a few specific problems that I've worked on quite a bit. And this is a regression problem where physical activity data, that complete 24-hour trajectory, is an outcome of interest. And we have a variety of functional predictors. I'll talk about dimension reduction, how you take complex objects like functions and reduce their dimension a little bit. And then I'll talk about registration and alignment, which is a problem that is in some ways unique to functional data analysis, or at least to problems where you have repeated observations on a subject and you want to be able to identify the major features across people. The motivation for function-on-scalar regression actually came from this plot, which had nothing to do with functional data analysis at the time. We took data from the Baltimore longitudinal study of aging and just characterized in 4 equally split age groups how much physical activity each group got in sort of like an average sense. And we saw that the youngest age group got the most physical activity. And then you started seeing as folks got older, there was a little bit of a decrease in physical activity. And then of course, quite a bit more as patients aged into their 70s and 80s. The reduction in physical activity wasn't uniform across 24 hours. It was sort of highest here. And then even as folks got older, there was a bit of a dip early in the day and a more extreme dip later in the day. And what's interesting about this is that it is possible here to sort of think about the amount of activity a person is getting as something that happens over the course of 24 hours with time-specific changes in relation to getting older. Now, the drawbacks to this is that we were doing something that was very exploratory. We sort of saw this age effect in a descriptive way, but we weren't able to adjust for things like gender or race, ethnicity. We couldn't take into account whether or not somebody had retired. There were a variety of issues here that made this interesting, but not sort of concrete in a way of understanding formal associations. And so that's really what we wanted to address through a regression framework, is not just whether or not something looks interesting, but is there actual association? Are there confounders that we need to take into account? Is there some measure of statistical significance? The data that I'm actually going to look at comes from 420 kids in the Head Start centers. Head Start is an early childhood education program in northern Manhattan in the Bronx. Accelerometers were worn on the non-dominant hand. It was attached to these kids with a hospital band, so they were sort of unable to take it off. We don't have to be super concerned about issues of taking the device off or non-wear or anything like this. The kids wore this device for 5 days. We're going to average across those 5 days to get 1 observation per child. And we're interested in understanding how things like age and sex and BMI, and also child behaviors, their TV, how long they play video games each day, whether it's a warm season or a cold season, whether the mom was born in the United States, how many other kids live in the home. There are a variety of things that we're interested in understanding here. And our goal in general was to try to understand what determined physical activity among kids in northern Manhattan and the Bronx. And in particular, is there some structure there that we could leverage if we wanted to promote physical activity? Is there some targeted messaging that we could have to say, here is a time of day in which this group needs to be a little bit more physically active? Our collaborators had taken all of this data and originally, instead of looking at it over 24 hours, had averaged everything down to a single number and said, this is the amount of physical activity that these kids are getting. And are there any associations that are interesting here? And I'll talk a little bit about that in just a second, and at least compare that to the functional data approach. In general, the concern that I have with that is that we actually have complex information. We know what's happening not just at a cumulative level, we actually know what's happening at every minute of the day. And so taking each of those trajectories and reducing it to a single number, I sort of feel like there is a good amount of information that is lost. And again, this is something that I'll talk a little bit more about in just a second. Our goal instead was to build a regression model for that complete functional activity outcome, the functional outcome of physical activity. And we're going to do this to sort of try to understand what covariates affect the timing and duration of physical activity. If you're going from a scalar response, just understanding what physical activity is as a total single number summary, and regressing that on age and BMI, you have sort of a very familiar multiple or linear regression in the top line. In the functional data setting, there is something that changes a little bit, which is that our response now is not a single number, but at least conceptually a complete curve. And so the coefficients that we're now interested in estimating are things like an intercept function that tells you, for a baseline category, what does physical activity look like at every time over 24 hours? What is the full diurnal pattern here? And then when you think about age, you think about age having an effect on physical activity, but that effect is also characterized differently at different times of day. It's not a single shift up or down. You might have some effect at 10 in the morning and a different effect at 10 at night. And so all of our coefficients, because the outcome here is a function, all of our coefficients are going to be functions that we need to estimate as well, but the covariates have stayed the same. Those are still scalars. And the interpretations here, I want to be clear, are also at least broadly speaking the same in the sense that this beta age of t is the effective age for each 1 unit change in age. while you keep everything else fixed. The model is more complicated in that it includes a temporal structure, but it is still in some sense a linear regression model. I said I'm not going to spend a lot of time talking about the technical details here, and I'm really not going to. What I think the thing that I want to express with this slide is that there is some amount of difficulty in re-expressing a functional data model into a form that's more familiar. But once you sort of do that re-expression, you end up being able to use tools that are very familiar. What I mean by that is, suppose our model for the observed data, I've constructed a matrix Y where each row is 1,440 minutes. I have that complete trajectory for subject 1 and 2 and 3 and 4. My X here is a usual design matrix of an intercept and whatever scalar covariates I have. And then the coefficient that I want to estimate is a collection of functions. The beta, the intercept, that's a function of time. The age coefficient is a function of time. The BMI coefficient is a function of time. And I'm expressing that using a spline basis theta, which I know, and then a collection of spline coefficients, one column for the intercept, one column for the age effect, one column for the BMI effect. And if you start with this model and you re-express it so that Y takes that first row, puts it as a column, takes the second row, attaches it next, the third row attaches it below that, you can actually re-express this entire model using a Kronecker product of my known design matrix and my known spline basis. So this is all one big known matrix, and then a vector of spline coefficients that I need to estimate. And leaving aside the sort of extra notation about having vectorized versions of things, this is a response vector, this is a known design matrix, and this is a vector of coefficients that I need to estimate. And this is something that one can estimate using ordinary least squares, or if you want to take into account residual correlation, something like generalized least squares. You can do some additional things to make sure that although you're expressing something using a spline basis, you can add in a penalization structure to ensure smoothness in the coefficients that come out of this. So there are, and I think a lot of work in functional data focuses on that, is how to model residual correlation and how to ensure reasonable structures. But the underlying method is, I hope, at least a little bit familiar. This is in some sense a way of thinking about doing a regression framework that's built on ordinary or generalized least squares. So I want to talk a little bit more about the outcome of the analysis that we did here. We fit this function-on-scalar regression model, and we wanted to look for effects of demographics, behavior, and mother-level covariates. We also looked at interactions between season and the child's sex, and between season and mother's work status. And some of this was motivated by our own model building. Some of it was motivated by the work that our collaborators had done already. The kinds of results that come out of this are the following. In the top row, I'm showing sort of all of the functional data separated male and female in this panel in the warm seasons and then in the cold seasons. And so if you do sort of a comparison within panel, you can see that in warm seasons, boys tend to be more active than girls, and that seems to be true. I'm showing pointwise means for each of these. That seems to be true over most of the daytime hours, but not, of course, in the evening or in the early morning. If you look at the cold season, the effect comparing boys to girls is greatly attenuated and probably not really existent at all. There is also a comparison of here, the warm season to the cold season. Everybody becomes less active in the winter months. In the bottom panel, I'm able to show the coefficient functions. This is something like beta of t comparing boys to girls. And you see sort of the expected effect. There is a decrease in physical activity for boys, a reduction in physical activity counts of about 100 or 150, and that seems to be pretty significant over all of the daytime hours here, and not significant if you're looking in the cold months. We looked at a couple of other things, and at least as a motivation for why I think this kind of physical activity data approach is helpful. If you look at something like TV use, does a child watch more than 2 hours of TV or not? Not surprisingly, the kids who watch more than 2 hours of TV are less physically active. Perhaps what is surprising is that looking at this from a functional data perspective, you can actually get a very specific understanding of when that happens. Kids who watch a lot of TV, it seems, are watching a lot of TV in the evening hours, and they're being noticeably less active than kids who don't watch a lot of TV. But during the day, you don't see really an effect at all, and then in the evening you do. And what's important about this is it gives us some way, not just of saying like you should watch less TV, but if we were going to target an intervention, if we were going to send the moms a text message or something like this that says, now might be a good time to make sure that your child is not watching TV, you can focus that at a particular time and promote physical activity in that way. I am going to point out, our collaborators had originally averaged across the 24 hours to get a single measure of how much activity is happening. And one might think, the average activity over 24 hours is very similar to just averaging the outcome curve or integrating across the time domain. And so could one sort of recapture that same collection of information by averaging across a temporal domain? And the answer in some sense is yes, you can. You can define average activity by integrating here, and you could also integrate the coefficient functions. If you use ordinary least squares, the correspondence here is exact. If you use generalized least squares, there's a little bit of a difference in the integrated betas here and what happens if you just fit a multiple linear regression, but they're often very similar. What is different is that that inference is a little bit different. And you'll see here a sort of a comparison of these things. And I'll point out, for example, the mother being born in the United States seems like it is insignificant, not a statistically significant association if you are looking at a multiple linear regression of the aggregate outcome. But in a functional data setting, it seems like there is some significant effect. And I'll sort of go back and see maybe why that is here. This is the coefficient function that corresponds to this. And if you're sort of thinking about the integral of this, there's a decrease in the morning in physical activity and an increase in the afternoon. And on aggregate, those two things sort of seem to cancel each other out. But if you're thinking about this just as a time-specific function, if you want to know whether this function overall differs from zero, the answer seems to be yes. It seems like there is, at least in this population, a shift among children whose mother was born in the US. They tend to wake up a little bit later and be a little bit more active in the second part of the afternoon. And again, this gives us some idea, if we're interested in understanding the structure of physical activity, timing might matter in this sense. You might see more activity here and less activity here. All right, so like I say, the multiple linear regression and the function-on-scalar regression are sort of both correct in this sense. You get some idea about what physical activity looks like. What you gain from a functional data approach is a bit of time-specific information, understanding when somebody is physically active and potentially being able to develop an intervention to promote physical activity around that. All right, I'm gonna shift gears a little bit and say, again, there are a lot of things that you can do in function-on-scalar regression, but rather than talk more about that, I want to talk about some work in dimension reduction. Accelerometer data, anything where you have sort of a high dimensional observation for each subject is complex and high dimensional. And it's also, when I say complex, what I mean is it's not just high dimensional. I don't have 1,400 minutes that are all independent of each other within a subject. There are temporal associations. Being active at 10 in the morning may say something about whether or not you're active at 10:15 or 10:30. Being active at 10 in the morning may also tell you something about being active at 6 in the evening. There's just some amount of temporal information that it's helpful to understand and to incorporate. So what we'd like to be able to do is extract that interpretable low dimensional structure, something like principal components analysis or another dimension reduction approach. But those dimension reduction approaches don't naturally account for that temporal structure. And that's sort of something that we would like to be able to do. The three things that I'm going to talk about today, first is NARFT, and I'll sort of say where that came from in just a second, and then generalized functional principal components analysis, and then a more recent tool that we've talked about, functional principal components pursuit. I'm going to make a brief digression on functional principal components analysis, which is a pretty well-established technique for dimension reduction in functional data. Functional principal components analysis is a variation on principal components analysis that involves smoothness in the eigenfunctions. And so here I'm sort of thinking that if we wanted to say that there is some subject-specific observation, and here I'm expressing this as a mean, although I've got an error term, that's a poor notation on my part, I apologize. If you're thinking about this as sort of like a subject-specific curve, I want to decompose that in terms of a population average and then a collection of subject-specific scores and shared basis functions across individuals. These are our sort of principal components where, again, I'm thinking of these explicitly as functions of time. And the incorporation of this as a function of time means that when we're doing this estimation in the same way that we did with a function-on-scalar regression, we want to be able to include some temporal smoothness, often using a basis expansion and some penalized estimation that enforces smoothness in the principal components here, as well as in the mean function over here. I'm going to revisit this data set, something like this, and talk a little bit about why we wanted to try something different from usual FPCA when we're looking at wearable device data. And the two things basically that I would point out, the first is that the previous model generally assumes that errors are going to be, if not normally distributed, then at least mean zero with a constant variance over time, and that outcomes can be both positive and negative. What we actually see in physical activity data is that everything has to be greater than zero. It's a non-negative data. And there is also something that looks a little bit different from a normal distribution. And we're going to try to develop a dimension reduction approach or dimension reduction approaches that take that into account. The first approach that I'm going to talk about is one that a student, Daniel Backenroth, came up with, and he labeled this NARFT, which I thought was a terrible acronym at first, but then it grew on me pretty quickly after that. He called this non-negative and regularized functional decompositions. And the idea here is to borrow from something that has become a very popular tool, especially in computer science, which is non-negative matrix factorization. The idea that if you wanted to do a dimension reduction on data that is non-negative, you can ensure that the prototypes, the something that looks like principal components, are non-negative, and then individual loading on those are non-negative also. And if you have sort of in this model a constraint that all of these are non-negative and all of these are non-negative, well, then ideally you end up with something that's a little bit more interpretable than something that can be sometimes positive and sometimes negative. Our argument, at least, is that this kind of an approach makes a lot of sense for accelerometer data, where we know all of the outcomes are going to be strictly greater than zero, and we're going to sort of try to build in functional data techniques, the smoothness across time, into this non-negative matrix factorization framework. The model that Daniel came up with says that the subject-specific mean here is a combination of scores, CIK, and prototypes. I'm being careful not to call these principal components. The model is different. Functional prototypes here that describe the direction of the patterns that exist in the data, and this should be subscripted by K, I apologize. And given these things, there's no subject-specific mean. We're going to sort of say everything starts at zero and multiplies the prototypes and then sort of adds up to become whatever that subject-specific mean is. And the observed data follows a Poisson distribution at each time point t around whatever that subject-specific mean is. All of these things are going to be things that we tried to estimate. The subject-specific mean is going to be reconstructed or constructed through adding non-negative scores to non-negative prototypes and sort of building things up from there. The estimation framework was, it took a little bit of time to get right, but the idea essentially is we have, in the same way with a functional data, Function-on-scalar regression model, we have data observed over a finite grid, and so we can sort of develop an iterative process using alternative minimization, where first we estimate scores given prototypes, and then we estimate prototypes given scores, and all of that sort of works in the context of observed data on a dense grid. And all of this, again, like the paper goes into details about all of the different ways that we tried to make this both efficient and stable. But that's sort of the basic idea, is to alternate between two processes of non-negative score estimation and then non-negative spline coefficient estimation while taking into account the overall data structure. I want to compare this, though, with a generalized version of FPCA, where instead of assuming that things are non-negative, here I'm just going to allow scores to be whatever they are and basis functions to be whatever they are. Here, because I'm sort of dealing with things that are not sort of all non-negative, I am allowing a population level mean in addition to a subject-specific deviation, but I'm still sort of thinking of the data as being distributed Poisson around whatever that latent subject mean is. Generalized functional principal components analysis, I think, is important. It's the subject of a growing literature. We did come up with a new way of estimating this that we thought was a little bit more stable. What's important about this is that I think there are a variety of trade-offs in comparing generalized FPCA to a non-negative estimation framework. The generalized FPCA tends to be more parsimonious. It gives you a smaller basis for explaining the same amount of outcome variability, but often the principal components that come out of generalized FPCA are just less interpretable, especially in the context of wearable device data. This is, the sort of recapitulates an argument in non-negative matrix factorization in general, which is in almost every domain that one might be interested in, having some non-negative structure often makes things a little bit more interpretable at the expense of being less parsimonious. And that's what we found as well. So I'm going to look at this in the Baltimore longitudinal study on aging. We had about 600 subjects. Here, instead of looking at 1 minute epochs, one minute time intervals, we aggregated to 10 minutes just to make this a little bit more computationally feasible. And we estimated principal components and prototypes using periodic B-splines. The results for NARFT here, the prototypes, the first 5 are shown in the top row. And you see things when I talk about interpretability. You see there's one prototype that mostly tells you about activity in the middle part of the day, one prototype that tells you about sort of the mid-morning, one prototype that tells you about the early morning. This one gives you sort of late afternoon and evening activity. Each of these, I think, is you can sort of look at and say, the prototype here is explaining variability in a very specific time of day. When you start looking at generalized functional principal components analysis, the first here is maybe interpretable as an overall increase or decrease. This sort of looks like a contrast maybe between early activity and something that happens later in the day. But then you start getting these sort of very wild oscillations, and it's just unclear what the interpretation, for example, of this principal component might be. So again, the trade-off here is, I think, interpretability for NARFT versus parsimony for GFPCA, and that's sort of roughly what we found. I'm showing here the sort of additive process that NARFT uses. If you take sort of score 1 times prototype 1 plus score 2 times prototype 2 plus score 3 times prototype 3 and so on, you sort of end up at a subject-specific reconstruction here. With GFPCA, you sort of, it's unclear what happens when you start adding component 1 to 2 to 3 to 4. It just sort of bounces around all over the place, again, in a way that I find less interpretable, although certainly more parsimonious. The last dimension reduction approach that I'm going to talk about is principal component pursuit. And again, we're sort of drawing on an approach that existed in the computer science literature. So in computer vision, often folks will see frames from something like a security camera. You have a observation here and another observation here and another observation here, and there's a relatively stable background, and then some people come into the frame and then out of the frame. Here are people here, and then some crowd going over here. And the idea for principal component pursuit is to separate out the low dimensional structure that is relatively unchanging from big outliers, things that are obviously different going from one frame to the next. And so if you can separate this panel into the constant background and then the things that are big and outlying in the background, that should give you both an understanding of what the low dimensional structure is and also some idea about whether or not these sparse outliers are interpretable. And that's what we're going to try to do here. In a functional data setting, the way that we're going to think about this is that outcome data Y has a mean and then a low rank structure that looks very much like principal components, scores, and then basis functions, and then some large outliers are sort of taking the overall error term and separating that into small sort of variability around a mean and then large outliers that are sort of stacked on top of those. The estimation framework is not super surprising. It's sort of iterative in the same way. You estimate the low, you sort of come up with some idea about what the sparse error is going to be. Given that sparse error, you can subtract out the large outliers and then do principal components analysis to get the low ranked structure. Then given that low ranked structure, you can see what error terms are sort of too large in magnitude to be plausible, just sort of noise around the mean, and you iterate between these two different things. We end up sort of, in following this original principal component pursuit algorithm, we end up with low ranked structures and sparse errors that are a little bit attenuated. And what I mean by that is the sparse errors are not the entire sparse error, it's sort of shrunk down a little bit, so you still see some impact of that in the estimation framework. I think I'm maybe going to skip this piece. The idea essentially is in doing whatever estimation you're going to do, you sort of introduce a sign function here that reduces the magnitude in some sense of the eigenvalues of whatever decomposition you're interested in. You sort of take your eigenvalues and shrink them down just a little bit. What is nice about this is some of those eigenvalues that exist here are going to be shrunk all the way to 0. And so this does give you some way of, at least in a data adaptive sense, of estimating the number of eigenfunctions of eigenvalues that actually exist in the model that you're interested in. And I guess what I do want to show are some of the results of this analysis, where we've taken physical activity data in the top row and estimated a low-ranked structure, something that looks like the 24-hour mean for an individual, and then separated out is, say, in this case, a very large error, something that seems like a noticeable deviation from the subject-specific mean here, put that into a sparse error term, and then had some amount of noise that exists on top of that. And again, our hope in doing this is that by separating out these sparse errors, we'll be able to say, for example, this is a bout of intense physical activity. This is when somebody has been noticeably physically active. They were running for the
Lola, there is some problems.
Sorry. I hope folks can hear me again. Let me share my screen. Okay. I apologize. The internet here has been a little bit unstable over the last little bit. I'm going to stop my video just to preserve a little bit of bandwidth. I hope everybody can still hear me. So if you can't, please let me know, but otherwise I'm going to sort of continue on. In registration, in functional data analysis of wearable device data, it's useful to acknowledge that people will wake up at different times and go to sleep at different times. And that's something that we've ignored in our analysis up to this point. And so one of the things that we're going to do here is try to align major features of the day, again, using some data adaptive process. And this is a subject of a large body of work in functional data analysis. I don't really have time to do a complete overview of that. But the things that we wanted to contribute in this is looking at data that pretty clearly does not come from a Gaussian distribution. And we also wanted to do this in a way that's very computationally efficient. So we looked at things like binary physical activity, whether or not somebody was active or not. And over the course of 24 hours, you see that people are asleep in the nighttime. I'm not sure where my cursor is. People are generally asleep in the nighttime and awake in the daytime. But there are major patterns. When somebody wakes up is different going from one person to the next. This is another way of viewing that same data, where instead of looking at binary activity, yes or no, I'm sort of making a plot that shows the probability of being active at a person level. You see one person is very active early in the morning. The other person, potentially somebody who works in the nighttime, is active later in the day and inactive in sort of normal daytime hours. The goal for registration is to try to understand how a single subject's time might be stretched or shifted to align major patterns to those of others. And so if I look in the figure at the left-hand side, I have the observed data for a single participant. And if I were able to stretch the chronological time on the x-axis in some way, then I might be able to make that person's major features align with those of somebody else. That middle function is the thing that warps chronological time for an individual to registered time that is shared across everybody, where registered time is the x-axis in the far right plot. And essentially what I'm saying is that in the morning, it seems like time moves a little bit more quickly for somebody, and then maybe in the afternoon, it moves a little bit more slowly for the person highlighted in red. But if I estimate one of these warping functions for each participant, then I should be able to align activity across everybody. And indeed, that's what we see in the far right side, or the results of this registration process applied to wearable device data. And the benefit of this is we both get some measure in the middle panel about what kinds of process differentiate the timing of physical activity. And then in the right, after registration, we can see the actual features that exist in the data much more clearly. It seems that everybody most everybody wakes up and is somewhat active in the morning. There's a midday dip, probably around lunchtime and a little bit after that, and then another peak in activity in the second in the afternoon before everybody sort of goes to sleep. And that's sort of the benefit here of doing registration. I've got an illustration here that looks at the warping functions a little bit more carefully. Essentially, we're taking chronological time, the observed data time, and stretching or shrinking that data so that the major features become aligned. And this is something that we spent a lot of time working on, especially in the context of binary physical activity, of looking at whether or not a person is active or inactive, rather than being particularly concerned about the intensity of their activity. I'm going to skip past some of the details here. The idea, sort of not surprisingly, is sort of an iterative process. One of those steps is saying that we want to be able to understand the structure of activity. We're looking at the binary principal components analysis. And then the second is, given some overall understanding of the kinds of events that are common, can I estimate a subject-specific warping function that maps one person's day onto a population level template? And like I say, I'm going to skip past some of these. This is another view of the results that we've ended up with. The left panel is a view of that binary activity plot that we had seen in the past, where white points are inactive and blue points are active. The left panel shows the raw data, and in the right panel, we're showing what happens after registration. The sort of black point on the on the left-hand side is when somebody wakes up, and the red point is the daytime interval midpoint, sort of a measure of the middle part of the day. And what I'm sort of driving home here is that after registration, we do see pretty good alignment of when somebody wakes up and when they go to sleep. And then we see a feature in the middle, this midday dip, that doesn't seem to correspond to what one might have obtained if you hadn't done registration. Sort of red points in principle should be very, very nicely stacked, and they're just sort of not. They're a little bit all over the place here. All right, so I want to spend in the last couple of minutes that I have available thinking about the work that I do in functional data analysis. And the analogy that I like to draw here in data science is to transportation, the ability to move folks around. In the 1910s, I believe, there were sort of two things that were happening in transportation science at the same time. There was the first flight, and then there was also the Model T. And the first flight was something that was available to a very, very small number of people. It sort of represented the very cutting edge in transportation science. And then in the right, the Model T was an advance that made an existing technology available to the broadest group possible. And the analogy that I draw here in data science is that there are some very cutting edge methods development that are going to be available to a narrow group, but it's also important to make existing tools, things that are well understood, available pretty broadly. And both of those are important contributions to data science as a whole. So when I think about my work in functional data analysis, the stuff on principal component pursuit, I think of as more like the cutting edge kinds of methods development, but TidyFun and other software packages are things that are a little bit closer to making something available to everyone. I'm going to very briefly review tidy data. The idea is that if you are thinking of the observations that you should have in each column a variable and in each row a subject or an observation, and then each cell in your data table is the combination of a variable and an observation. Functional data, it turns out, are difficult to put into this tidy data framework because you have conceptually a single function, a 24-hour observation, one 24-hour for each person. But in principle, in actual practice, what you have is 1,400 minutes during the day. And putting those 1,400 minutes in the day into a data frame, into a nice organized data rectangle, turns out to be a little bit of a challenge. And especially becomes challenging if you start trying to work with data that are complicated and high dimensional structured in this sort of a way. And you're trying to work with this in, a data wrangling or processing or exploratory data structure. So that's what the TidyFun package is intended to help with, is a way of including functional data in a data frame in a way that can be used with other tools that come from the Tidyverse. So we introduce a new data structure, and then we also provide tools for interacting with those. And I think instead of showing all of this, what I'm going to try to do is show how this works in practice. So this is always a little bit of a challenge, but I'm hopeful that everybody can see my screen. I'm looking at RStudio, and I'm going to load 3 packages, tidyfun and the tidyverse, and we also have a package refunder or a variation on refund. And I'm going to load here a CHF data set that includes physical activity data. And if I just look at the CHF data frame, you'll see that it includes some number of variables. Hopefully everybody can see this. It includes some variables that are very much regular. You have a subject ID, you have their gender, their age, their BMI, but we also have an activity column here that includes an entire functional observation. It says for subject 1 at minute 1, there were 0 activity counts. For this subject at minute 1, there were 4 activity counts. For this subject at minute 3, there were 5 activity counts, and so on. But what I have here is a single column that includes the entire functional data structure. And tidyfun allows you to have things that are dense for each subject, sparse for each subject, whatever it is you're interested in. And since I'm running out of time, I'll try to show an example of the kinds of things that you can do with this to illustrate why one might be interested in this. So I could, for example, take my CHF data frame and do a usual data filtering step where I want day is equal to Monday. I might then take this and select just some of the columns that I'm interested in, maybe ID and gender and activity. I might from there do something like ggplot, where I have the response that I'm interested in is this activity curve, activity. And then I'm going to do geom_spaghetti to make a spaghetti plot of the CHF data frame on Monday with gender and activity. And maybe I'll do one more and set this color equals gender. And if I run this whole thing, what I end up with is a plot that's a little bit difficult to read here. Maybe I'll set alpha equals 0.1, but I'm looking at all of the physical activity data that I have here on Mondays for men and women in this data set. This is a spaghetti plot of log activity count, and so I could, for example, take activity is the raw activity count by exponentiating. And we might see something that looks a little bit more familiar to us. Yeah, you can sort of see the evening dip in activity, the daytime peaks. There are some large outliers in the activity values. You get color by male and female and a variety of other things. There is a full website that overviews the kinds of things that you can do with a tidyfun package. The idea in general is to make this as accessible as possible to work with functional data. And I encourage you, if possible, to take a look at that. It's at tidyfun.github.io, and I may have a link to this here. No, unfortunately, I don't. If you're interested in learning more about tidyfun, please let me know. If you have any questions about the papers that I've talked about today in functional data analysis, I'm more than happy to chat about that. I'm going to try to turn my video on again. I apologize that I haven't been that I've had a little bit of connectivity issues. And again, I really wish I was there in person, but if there's a way to ask questions now, if folks have them, I'm more than happy to hear those. Thank you very much for your attention.
Thank you very much, Jeff, for this useful, interesting, and light talk. I think we learned a lot today. Now it's time to questions. I don't know if you have any questions. People connected by online can ask too.
Hello, it was a very interesting talk. I was just curious if in the NARF model that you mentioned, when comparing it with functional PCA, in functional PCA you've got the extra restrictions that the scores, the loadings are orthogonal. Given that the NARF loadings are required to be non-negative, I was just curious if well, I guess that the orthogonality restriction is lost, and I was curious if this affected the variability that each component was able to recover.
Yeah, it's a very good question. I'm going to try to share my screen again and make sure you can see, everyone can see what I'm talking about. So here, if we're thinking about NARFT, you're right. These prototypes are something that are non-negative, and in that sense are we're not able to impose a usual orthogonality constraint. And so the interpretation of how much variability is explained by the first prototype or the second prototype or the third, it's difficult to do that sort of a usual decomposition. In generalized FPCA, you can look very quickly at the eigenvalues and know how much variability is explained in some sense by the first principal component and the second and the third. There are some ways here that we have come up with something that tries to get at the same question. You can look at something like the overall contribution to the outcome likelihood of all of the scores for across all of the subjects multiplied by that first prototype, and try to sort of do something that's a little bit more ad hoc. But you're right, because we don't have an orthogonality constraint, we don't get a very easy partitioning of the outcome variance. There's actually, I guess, one of the things, it's somewhat related to the orthogonality constraint, although sort of a more general issue that I didn't say as I was going through, but that I do want to be clear about, is because we're allowing both for non-negativity and we're not introducing an orthogonality constraint, there are some issues for model identifiability in NARFT and in non-negative matrix factorization in general. There are conditions under which everything is well identified, but it's always unclear in practice whether or not those conditions are going to be met. One of the things that we did here, we did a variety of sensitivity analyses to make sure that NARFT was converging to basically the same solution each time. We did a variety of data splits. We tried a variety of initial conditions. It seems like NARFT is stable numerically, but it doesn't come with the same guarantees that generalized FPCA does. Okay. Thank you for the question. I appreciate it.
Thank you very much.
Another question? Yes, I have one. When you propose methods to dimension reduction, are you thinking in the possibility to generalize the PLS dimension reduction using the information of the variable Y?
Yeah, that's a really good question. There is some collection of work in functional data analysis, of course, that does that sort of an approach, a penalized least squares or a partial least squares, something that tries to get at a dimension reduction that is informed by an outcome of interest. Here, that's not usually what I've done. In part, that's because I more often think about, in part, that's because I sort of think about the physical activity data as something I want to model potentially across a variety of outcomes that I might be interested in, or a variety of predictors that I might be interested in. And so I sort of like to separate, again, as a personal preference, I like to separate the dimension reduction piece from the association with other variables. But I think in general, those tools have worked pretty well. And I think there's a lot of room to generalize them to this functional data setting, and especially functional data for wearable devices. There's a good collection of ideas, not something that I've thought a lot about myself, but I think would work pretty well. Okay.
And when you consider the behavior variables in the model as the 2 hours of TV or something else, who provide the information about this variable? The child in a questionnaire? Or?
Yeah. So in general, the scalar information that we get, the demographics on the child, the information about the mother, the number of other kids in the home, the family income, race, ethnicity, amount of activity, TV that a child watches, all of that does come from a questionnaire. So we're getting better measures of physical activity than we've gotten in the past, but there are a lot of measures of other kinds of behavior that we're still mostly relying on self-report. And it may be inaccurate. It may be that folks tend to be, a little bit less likely to be honest about how much TV they're watching when they're participating in a study like this, but it's sort of the best that we were able to do on those variables.
Okay. Any more questions? Then we thank again to Jeff.
Right. Thanks, everyone.
No, sorry, Jeff, there is one question more.
Okay.
Thanks, Jeff, for your presentation. It was very interesting. So I have a very little question. Okay. I'm Daniel Precioso. So nice to meet you. I'm a PhD student on computer science. So I have a little question about your time series processing. You told us that you have activity data and you convert it to binary data. I was just curious about how you perform that binarization.
Yep. So that's a good question. So the physical activity data that we get is something like the amount of activity that a person gets over the course of a 1 minute time interval. And I'm being a little bit vague there because it's not always clear how one obtains that minute level amount of physical activity that a person gets. Maybe I'll sort of scroll and show, right? So how one goes from an accelerometer device that's worn on the wrist to the value that appears on the y-axis here is not always super clear. And I can talk a little bit more about that if that's what your question is. But what often happens is if you want to go from activity here to sedentary or not, is a person active or not, you can apply a relatively low threshold here, somewhere around 10 or 20 physical activity counts on the y-axis will give you some idea about whether or not a person was active or inactive. I think we chose 10 activity counts as the threshold, and we did a variety of sensitivity analyses to see whether our results changed noticeably if you shifted that threshold down a bit or up a bit. And as long as you stay within some reasonable range in this part of things, you get very consistent results.
Okay, many thanks.
Thank you.
Okay. Then now is the last question. Now we thank again to Professor Jeff, the very good, nice